Alrighty, let's go ahead and we're probably going to do 2 more videos. So this is part 5 of 6. I'm just going to run through some examples, and I'm actually going to introduce definite integrals here in just a moment. But let's go ahead and do x squared root 1 minus x dx. Now at this point you should start getting sort of a feel of when a certain strategy needs to be entailed. At this point we should see the fact that 1 minus x, if I go with my default that my radicand is going to be my u, which it usually is, I can go ahead and say, well, u is equal to 1 minus x, x is equal to 1 minus u, and x squared is u squared minus 2u plus 1. And I also know that du is equal to negative dx. Okay, so you can sort of put all that sort of into a little box and use that to transform this. And I'm going to take this negative right here because that just means that negative du is equal to dx, right? So I can, either way, but if this actually makes more sense to you because you're actually taking out the dx and plugging in the negative du, I'm going to put the negative out here in front, okay? And in doing so, I'm going to get u squared minus 2u plus 1 times u to the 1/2 du, okay? Now that I have that, it should be fairly straightforward because I can distribute. Now that that radical is a monomial, have a monomial radicand, I can make it in terms of a single variable raised to a fractional exponent, and that is distributable. And now that I have distributed as like this, I can go ahead and integrate term by term by undoing the power rule. Okay. Now if you want, you can actually take this negative and make it a part of each of those terms, so you don't have to do both of those steps at once. I know that it's going to be negative 2/7 u to the 7/2 plus 4/5 u to the 5/2 minus 2/3 u to the 3/2, and that plus c isn't going to fit on there, but we'll sort of drop it down right there. And then I just have to take that expression right there, which is our u, and plug it back in. 1 minus x to the 7/2 plus 4/5 1 minus x to the 5/2 minus 2/3 1 minus x to the 3/2 plus c. And that right there is my integral. Sometimes the back substitution can wind up being a little bit messy. That wasn't too bad. Let's go ahead and move on to another one. This one will also require a little back substitution. Okay. So if I make u is equal to 2 minus x, I know that du is going to again be equal to negative dx, or negative du is equal to dx. That's easy enough, right? Now from here, I can go ahead and change this into x 2 minus u, and then of course x plus 1 is equal to 3 minus u. Now that doesn't require quite as many terms as the previous one because the last one had an x squared. You were squaring it. So from here, this simply becomes, and again, like the last time, I'm going to take that negative from the du. I'm going to pop it out in front because I can. And I get 3 minus u times u to the 1/2 du. And actually, I tell you what, let's take that negative and let's use it to flip the order around right here as I'm distributing. And so if I take that right here and make that u minus 3, that's going to become u to the 3/2 minus 3u to the 1/2 du. From here, the integration, as we've talked about before, is rather straightforward. Okay. Now this is going to be u to the 3/2 over 3/2, which means multiplied by 2/3. But when that 2/3 combines with the 3, it's just going to be 2 that's left. And then you have plus c. Then as we've done before, you just have to substitute back the expression for u, and there we go. Okay? Now, we've done that before, but like I said, I'm going to, in this video, introduce the definite integral. The definite integral, you would think, oh gosh, well that was hard enough. Definite integral is going to be even harder. Actually, the great thing about this is that, at least in one way, the definite integral is actually easier. And I'm going to show you why. Well, let's go ahead and say, well, yeah, let's go ahead and see whether that's going to be u1 minus x squared, okay? And you know that du is going to be negative 2x dx. And so you know if you change this into negative 1/2, 0 to 1, square root of 1 minus x squared times negative 2 dx, that makes it very, very easy, right? So that's u to the 1/2 du. So there's no back substitution. That x was actually part of your du. You just had to sort of, pick it up and put it over here next to the dx. Now here's the thing. The moment that you substitute, you can no longer use 0 and 1. Because 0 and 1 refer to x values. The moment that you've changed the integrand into u values, you need to do one of two things. You either need to integrate and turn it back into x before plugging in your x values, or you need to change your limits of integration into u values. And that's actually the easier way to go. So I know that radical right here becomes u to the 1/2, and that becomes du. And you just need to ask yourself a simple question. Well, when x is equal to 0, what's u equal to? Well, 1 minus 0 squared, or 1. When x is equal to 1, what is u equal to? 1 minus 1 squared, or 0. Well, all that takes in order to turn it into a nice, neat integral is to flip the limits of integration and take away the negative that's out in front. And so I have negative 1/2, 2/3 u to the 3/2, 0 to 1, or 1/2, 2/3 0 to the 3/2 minus 2/3, or sorry, that should be 1. 1 to the 3/2 times 0 to the 3/2. Okay, that is obviously 0. 1 to the 3/2 is obviously 1, so it's 1/2 times 2/3, or 1/3. You don't have to change it back in terms of x. You can actually leave it in terms of u, so long as you have changed your limits of integration to match up in terms of u. Okay, and that's the trick right there, and that's why the definite integral, when it comes to u sub, people go, oh no, and then you show them, and they're like, oh, that's really not all that bad. And the answer is, it really isn't that bad. Okay, so let's go ahead and go through another one. Okay, now again, my desire, my gut reaction is, man, I really want to make 2x minus 1 equal to u. Okay, and the thing is that it actually does work. There wind up being a few fractions involved, but that really shouldn't be all that worrisome. U plus 1 is equal to 2x, so x is equal to 1/2 u plus 1. Well, I also know that du is equal to 2 dx, or 1/2 du is equal to dx. There are my little pieces right there. So what I need to do is I then need to sort of plug it in, right? Well, what's x equal to? X, which was the original numerator, the new numerator becomes the u expression equivalent of x. Since u is the radicand, u to the 1/2 becomes that denominator. Okay. Now, I know that dx is equal to 1/2 du, so we'll plug in 1/2 du in for x. Now, before we clean this up, we need to be very clear. We cannot make 1 and 5 the limits of integration here, unless they just happen to be by some weird coincidence. I have to transform 1 and 5 from x values into the corresponding u values using this relationship. So when x is equal to 1, meaning plug 1 in, I get 2 times 1 minus 1, or 1. Okay, we'll plug 5 in. 2 times 5 is 10, minus 1 is 9. So when x is equal to 5, u is equal to 9. Okay. Well, now we're going to go and take this 1/2 and this 1/2, and we'll pull both out in front. Okay, and then we just need to simplify this rational expression that has a monomial denominator. We have u to the 1/2 plus u to the negative 1/2 du. So that winds up being 1/4. And then we'll have 2/3 u to the 3/2 plus 2 u to the 1/2. And we're going to evaluate that from 1 to 9. Well, that difference might be a little bit difficult to sort of, parse out, but just let's, it shouldn't be too hard, right? First, we need to plug in 9. Now remember, when you're raising it to a fractional exponent, always do the root first. What's the square root of 9? Square root of 9 is 3, and then 3 cubes. That's 27. But then it's 27 times 2/3. 2/3 of 27 is 18. Okay, now I just need the square root of 9, which is 3, times 2, which is 6. Then I need to subtract when I plug 1 into here. And of course, plugging 1 into there is going to be extremely easy. Okay, so what we have here is basically this winds up, and of course, if you just want to, get rid of the parentheses, you can go 18 plus 6 minus 2/3 minus 2, and that makes it a little bit easier because basically you're going to get 22 if you combine all the whole numbers or integers. 22 minus 2/3, which is 21 1/3, okay? But if you have 22, 22 in terms of thirds is 66/3, minus 2 is 64/3, so it's 1/4, 64/3, or, and that is that of course in that form is much easier to simplify. That's going to be 16/3. Okay. Now, there is a little bit of computation, and with the fractions and everything like that, there's a possibility of it actually making careless errors. But in terms of conceptual richness, there really isn't a whole lot more going on here than there was going on in terms of the indefinite integral. Let's go ahead and do one that's a little more straightforward. Well, depends on whether you think trig is a little more straightforward, I guess. But it actually doesn't have as much going on in that particular one. We know that sine to the 5th 3x cosine 3x dx, for those that are sort of uninitiated in trig, that looks rather nasty, okay? We just need to remember that that is that, right? We can take that and put brackets around it and put that exponent up here because that's actually what it means. Okay, so if I know that u is equal to sine of 3x, because remember my default is at least to say, well, it's probably the thing that's in brackets or parentheses raised to the power. I know that du is going to be 3 cosine 3x dx. Now from here, the only thing that needs to happen in order to get it into the proper form is you need to drop a 3 in right here, and then that requires a 1/3 out in front. But that isn't a whole lot of work to do. You've done a whole lot worse, right? So I know that it's going to be 1/3 u to the 5th du. But again, these limits of integration are in terms of x, okay? What I need are in terms of u. So I need to know, okay, if I plug in 0, okay, sine is going to give me 0. If I plug in pi, sine of 3 pi is again 0. Well, I know that I probably don't even have to figure this one out. I probably can just go ahead and put 0 right there, okay? Now, what that means in terms of, if you want to think back to our original way of thinking about, if you want to go back and think about our original way of thinking about the, integrals as the area under the curve, well, let's go ahead. 3x, and let's raise that to the 5th times cosine of 3x. Okay, well, let's go ahead and zoom in just a little bit. And if I'm going from 0 to 3 pi, let me go ahead and just change that just a little bit. I know that 3 pi is approximately 3 times 3, so it's close to 10. Okay, what I need to figure out is what happens between 0 and 3 pi. And the thing is, the reason why the answer for the area under the curve, or the answer for the integral, is 0 is that for every pi over 3, you have as much above the curve as you do below the curve. So in order to get a net area of 0, you simply have to have you have to have both limits of integration basically give you a certain number of periods, okay? And that's basically what's going on there. You're having just as much positive area as you are negative area. That pretty much sums it up for video 5. We'll do video 6, and it'll be a couple more indefinite and a couple more definite integrals to sort of round us out. Alrighty?